You know, I was reading about this centuries-old geometric puzzle the other day, and it just completely blew my mind. It starts back in the late 1600s with a prince, Prince Rupert of the Rhine, who makes this seemingly impossible bet.
Oh, the cube problem. It's a classic.
Exactly. He bet that you could cut a hole in a solid cube and then pass an identical cube right through it.
Right, which sounds completely wrong. But the answer, which came from the mathematician John Wallis, was, yes, you absolutely
It
can.
gets even stranger.
It does.
Huh.
About a century later, a guy named Peter Newland calculates the perfect angle and shows that you can pass a cube through that's actually 6% larger than the hole.
That's the part that breaks my brain. And this whole idea is called the Rupert property, right?
That's the one. And because it worked for the cube, and then for all the other Platonic solids, the dodecahedron, the octahedron, you name it, everyone just sort of assumed it was a universal rule.
So the conjecture was that every convex solid has this property.
For centuries, yes, that was the working assumption. Which brings us to the whole point of our deep dive today. The paper that finally, after all that time, proved it wrong.
And they did it by creating a shape with the most perfect name ever, the Noperthedron.
I love the name. It's so direct. Nope plus Rupert.
So this paper comes out in August 2025 from Jakob Steininger and Sergey Yurkevich, and it just closes the book on this ancient question.
Well, it closes one book and opens another. But yes, they designed this incredibly complex object. It's not a simple shape.
What does it even look like?
It's often described as looking like a really ornate, kind of rotund crystal vase. It has 152 faces, 150 triangles, and 2 big pentadecagons on the top and bottom.
So it was specifically engineered to fail this test.
It had to be. To prove a shape is Rupert, you just have to find one angle that works. But to prove it's not Rupert, you have to prove that for every single possible orientation, it fails.
Which is an infinite number of possibilities.
Exactly. A vast 5-dimensional space of angles you have to search.
Before we get into how they even began to tackle that, let's just take a quick moment to thank our sponsor. This deep dive is brought to you by Embersilk. If you need help with AI training, automation, integration, or software development, or just want to uncover where AI agents could make the most impact for your business or personal life, check out embersilk.com for all your AI needs. Okay, so proving a negative across an infinite search space. How on earth did they manage that?
Well, this is where the real beauty of the proof lies. It's this marriage of pure mathematical theory and some pretty serious computational power.
They didn't just brute force it then.
No, you can't. They partitioned that huge parameter space into millions of smaller regions. I think it was around 18 million distinct regions that had to be checked.
14 million, and they checked each one.
With theorems. Not just by calculation, they developed 2 main tools. First was the global theorem, which, handled the easy cases where the shapes are rotated far apart and their shadows clearly don't align.
Okay, that makes sense. That clears out the obvious no answers.
Right. But the real genius was in the local theorem. That's what they designed for the incredibly difficult cases, the ones where the rotation is tiny and the 2 projections look almost identical.
The near misses.
The near misses. And the Noperthedron was specifically designed so that its geometry made this super rigorous local theorem applicable everywhere. The proof ran on a computer for about 30 hours straight, verifying every single one of those regions.
So the Noperthedron doesn't just end the conjecture. It sounds like it forced them to invent new mathematical tools.
It really did. And here's the final twist, which I think is so cool. As part of their research, they also constructed a shape they called the Ruperthedron.
Okay, so that one does have the Rupert property.
It does. But, and this is the key, it is not locally Rupert.
Wait, okay, unpack that. What does not locally Rupert mean?
It means that if you only check for solutions where the 2 shapes are almost perfectly aligned, those tiny local rotations, you won't find one. The hole that works is at some completely different non-intuitive angle.
Ah, so that proves that you can't just check for the easy, nearly aligned solutions and call it a day.
You can't. It shows the true complexity of the problem. Finding the Noperthedron wasn't just about finding one exception. It was about building this whole theoretical framework to understand why. It's just a beautiful example of how a simple, centuries-old question can lead to brand new insights, all by combining pure thought with modern computation.
If you enjoyed this deep dive into geometry and computational proof, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.